Hello, I'm Riccardo Rizio of Collins Aerospace of UTRCI, and I'm here today to present the Smart Aerospace use case in the Shoot project. Our use case revolves around the interaction between the aircraft and a ground station server. Specifically, we will look into the secure server router located in the cockpit of the aircraft and the ground station server. Currently, the interaction between these two elements are purely wired and requires engineers to be physically present on the aircraft in order to perform any action on the SSR. Within this project, we are focusing in increasing the remote capabilities between the devices and all the actions that involve them. As a consequence, all the communication needs to be secure, the engineers need to be properly authenticated, and the device needs to be attested. For this demonstration, we will focus on the initial steps of user story number 1, where an authenticated engineer would like to perform a remote update on the SSR from the ground station server. In the image on the left, you can see how the setup would look like. We will use a Xilinx UltraScale platform for the SSR and a Raspberry Pi 3 for the ground station server. The elements represented in pink are the ones provided by the Azure framework, while the green ones are the binaries being executed on the devices. To ensure further security, we will use the OptE on both devices. Here presented, you can find the sequence diagram of the full user story. The GSS will act as the verifier, while the SSR will be the approver. When the engineer would like to perform the update, he will have to be authenticated by the framework first, then ask for the policy related to the remote update and execute it. In this case, the policy involves three main steps: checking the current status of the SSR before launching the update, downloading and executing the update on the SSR, and recontrolling that the SSR is still functioning as it should after the update. The attestation mechanism used to check the status of the SSR is the configuration integrity verification. In this demonstration, we will focus on the initial configuration integrity verification check of the binaries operating on the SSR after a policy has been uploaded to the blockchain. Starting from the verifier, the policy is requested to the security context broker and then shared to the attestation agent on the prover. This will read the policy details and, in this case, will execute the CAV procedure to attest the binary on the SSR. The CAV will request the traces of the binary, which will be signed by the TPM and shared back to the attestation agent, which will compare them with the known golden hashes. The attestation result is then uploaded to the blockchain for traceability. We will now showcase our demonstration. We have three elements to showcase: the prover, the verifier, and the security context broker. Starting from the prover, on the left side we have the TPM server, TPM client, the tracer, and the attestation agent. On the bottom we have our binary running and a script that allows the tracer to analyze our binary. On the right side we have the security context broker on top and two verifier elements, the blockchain RPC client and the attestation agent. We will now start with the demonstration, activating all the components. Starting from the prover side, we will activate first of all the TPM server, followed by the TPM client. Then the tracer, the attestation agent on the prover side, followed by the attestation agent on the verifier side. We'll then activate the security context broker client. We wait for it to be active, and it is now waiting for more information. We will now run our binary on the prover side, and we will enable the tracer to analyze our binary. And now we will set the whole framework in motion by submitting the policy from the verifier. All the console will show some operation, as you can see, and now we will go through them slowly. Starting from the verifier policy that was sent, the attestation agent received the request, share it with the prover. That requires the tracer to analyze the traces of the binary. The traces has to be signed, so they are sent to the TPM. The traces signed are shared with the tracer that are shared with the attestation agent on the prover side. They are sent back to the attestation agent on the verifier side, which double checks them with the golden hashes, and the result is then saved on the security context broker blockchain. Now we will see that the result is true because the traces generated in real time for the binary matches the one of the golden hashes. Thank you. Thank you very much for your attention, and I wish you all a very good day.